Hello students, welcome to another lecture of environmental modeling and simulation. In the last lecture we were discussing autocatalysis and how we can use the principles that we have studied so far to understand how autocatalysis behaves. We developed a phase portrait and today we are going to use the phase portrait to draw A versus T diagram for any initial values of A. So, this was the system we had last time. A plus x is creating 2A, x is your substrate, it is available in plenty. So, we can say the concentration of x does not really vary. Then the system that we came up with was dA by dt is equal to forward reaction minus backward reaction. Forward reaction is K1Ax minus K2A square. I have removed the square brackets here. It is understood that the units of A and x are in standard units. Since x is a constant, we can either replace x with a small x to denote that it is a constant, or in this case, since it is understood, I am going to leave it as such. We figured out that there are two fixed points for this system and the fixed points look like this. So, remember we are drawing a phase portrait and this is a one dimensional system. So, on x axis we will have our variable and on y axis we will have the rate at which it is changing dA by dt. We had two fixed points. The first one was 0, the second one is k1 x by k2. X is a constant, k1 and k2 are constant, all three constants are positive. So, we know for sure that the second fixed point is also positive. We also figured out that the plot will behave something like this. We do not know exactly where it will peak, we do not know if it will be a big curve like this one or a small curve like this one. This is a qualitative approach. So, questions like this we cannot answer, but we can understand a general behavior of the system. So, we also knew that 0 is an unstable fixed point, the second fixed point is a stable fixed point. So, now we can go ahead and we can start drawing the A versus T diagram. By now you must be very familiar with how to go about these diagrams. On x axis you have time, on y axis you have A. Once again, if you are starting at A equal to 0, the initial concentration of A is 0. It is a fixed point, even though it is an unstable fixed point, it implies that the concentration of A, if at beginning is 0, is going to stay 0. If you are starting slightly to the right of the A, notice that dA by dt is positive, which means the concentration of A, let us say we are starting here, A naught 1, the concentration of A will increase. So, the slope will be positive, this slope. The slope of the curve that we are drawing at this point will be positive. Now, as A grows, in the phase portrait, we are moving towards right hand side because A is increasing. And notice as A increases, the value of dA by dt also increases for this particular initial point. So, basically as A increases, the rate at which it is increasing will start going up. So, we are here facing a situation of acceleration. So, we will notice an exponential type growth. There is acceleration going on until the A reaches this midpoint. When A reaches the midpoint, dA by dt reaches the maximum. Well, I am not sure if it is a midpoint, we will have to do quantitative analysis for that, but basically when we reach the peak of this curve, dA by dt would have reached its maximum and we cannot expect a faster growth. We cannot expect further acceleration. But dA by dt is still positive, so the slope of the curve here will still be positive. The value of A will not reduce, it will only increase. Now, since it is still increasing, A in the phase portrait will continue to move towards right hand side in the direction of plus infinity. And what we will notice is that while dA by dt remains positive, the magnitude starts going down. The rate at which A is changing is still positive, which means the A will continue to rise up, but the slope, the acceleration is no longer there. In fact, A is decelerating. So, the slope that we will expect here now once it has reached the peak will be flatter than the slope before it, and this will continue. The same behavior as A continues to increase, and as it approaches the second fixed point, the curve will flatten a lot. And then at time t equal to infinity, or at sufficient time, which we also call steady state because now things are not appearing to move, A will stabilize around this fixed point, this concentration, which here is K1x by K2. If we draw an initial value bigger than the second fixed point, so let us say we are starting from here. Now here dA by dt is negative. Since dA by dt is negative, A will move towards left hand side direction. A is reducing, moving towards minus infinity. So we will see that our curve will slow down. So I am going to draw the upper part of this graph on right hand side here, because there is not space, there is not sufficient space here. So x axis is still time, y axis is still A. Let us say here we have K1x by K2, and our curve that we have drawn earlier looks something like this. Start at 0, stay at 0, start at a small enough value, and you finally stabilize around K1x by K2. Since K1x by K2 is a fixed point, if your initial value is here, let us call it A naught 2, then the concentration of A will not change with time, it remains constant. This is the definition of fixed point. Now what happens if we start here at A naught 3, where A naught 3 is bigger than the second fixed point, dA by dt is negative, which means the slope will be negative here. Now as A reduces, notice what happens. As A reduces, dA by dt is still negative, but the magnitude of dA by dt is going down. So yes, A is reducing, but the reduction is slowing down. So the slope of this curve here will be less steep as A reduces. So here let us say this is approximately, theta is approximately 45, and then it will start flattening out. And as A continues to reduce, it gets closer to the second fixed point, dA by dt will become smaller and smaller, almost approaching 0. So this is the kind of curve to expect. If you notice, this looks very similar to logistic growth qualitatively. Quantitatively, it is slightly different from logistic growth, but well, it is actually exactly same as logistic growth. It depends upon the concentration of K1A and K2, which will determine on also the constants in logistic growth, which would be R and carrying capacity, which would determine how quantitatively these curves look different. Qualitatively, it is quite similar. Now we are going to look at another one-dimensional model. It is also a growth model. It is called Gompertz model. Gompertz model is used to understand growth, especially in context of economics, marketing, and also in medical sciences, and in certain cases in environmental sciences. We use Gompertz model. Gompertz model behaves very similarly to logistic growth model, but there are very important differences. Since we are following nonlinear dynamics by Stephen Strogatz, we are going to take an example of the book and use a medical example that is given in the book. But do not worry, you do not need to understand medical science to understand this model that we are studying in environmental modeling and simulation course. So the Gompertz model, growth model, looks something like this. dN by dt, where n is number of anything, it can be number of residents in a city when you are looking at how cities expand to calculate how much water they will require over the next 20 years, 50 years, and maybe even longer. Gompertz model is one of my favorite models to teach people how we write models. For example, in this course, most of the times I will give you the models, or the question paper will give you the models. But in real life, you may run into scenarios where previous models do not exist for the scenario that you are trying to model. Now here, some of you may say, hey, we can look at other models that solved similar problems and start from there. And I think that's a brilliant approach. But there is also a way of writing models de novo, where you write models from scratch. Now if we look at logistic model and compare Gompertz model for a bit with it, so both of these models will give us very similar curves that we will see very soon. However, they look very different. On LHS, left hand side, both models have the rate equation dN by dt. But on right hand side, they look very different. So let's start with the model that you are already familiar with, the logistic model. If you look at the logistic model, on the right hand side, it comprises of two terms, one here, one term here. So, the rate at which number will change, number of bacteria, number of any contaminant, number of people in a city will change depends on these two factors, because there are two different factors that we have written. Now, notice that these two factors are separated by a subtraction. Whenever we have a plus or a minus sign separating two factors in a model, you can be quite confident that these two factors are happening independently, that these two factors represent phenomena that are happening in real life, but they are sort of happening independent to each other. Clearly, if you remember the exponential growth model, the first factor here is about binary fission in case of bacteria, or the forces that drive exponential growth. So, this could be the rate at which a species replicates or a strain of bacteria replicates. Now, the second factor here, notice that we are using the sign minus, which means the second factor is slowing down the overall growth or the value of the first factor, because we are subtracting some value from the first factor. But this factor is sort of independent from the first factor, which may represent exponential growth, which may depend upon biological limits, biological behavior. And we know from our understanding of logistic growth model that the second factor here talks about limitations of resources. In certain species, as the resources are limited, we run out of the resources, it does not change the biological behavior or the biological limit of the species. The species can still produce offsprings or daughter cells in case of bacteria at the same replicating time. However, limitation of resources will start having effect on the net growth rate. So, what you are seeing here is growth rate is equal to biological reproduction rate minus resource limitation. And these two factors are not intertwined with each other. They are not affecting each other. Resource limitation does not affect the biological production of daughter cell, does not, at the rate at which this is happening, does not affect the resource limitation. However, N does. Now, let us look at the Gompertz model. In Gompertz model, we again can say we have two factors. Now, there are multiple ways we can write these factors, and I will talk about each of the ways and say and show you which way makes most sense. Once you understand how to put different factors together, if you can model different factors, you can put them together using plus minus sign or multiplication and division, and then create your new models. That is what I want to clarify here. So, if you look at the first one, we can split this into two ways, in many different ways. So, first way could be to say that the first factor is minus a n, and the second factor is log b n. So, clearly this is showing some kind of decay, this is showing some kind of increase in number. The other possibility is we write a n is the first factor and log 1 by b n is the other factor. Now, if we write it in this way, the second way, this represents very clearly the biological growth rate. So, if we are using this model to understand how certain cells grow, we can say, well, this resembles biological growth, which is something that is to be expected by biological entities, whether they are cells, eukaryotic cells or bacteria or human population or population of some other animal. So, here it resembles biological growth rate. The second factor is log 1 by b n represents another factor, another phenomena which is combined with the biological growth rate by a multiplication sign. Now, multiplication sign differs from plus and minus. In plus and when factors of phenomena are brought together by plus and minus, these phenomena are happening because of independent processes. They might still have commonalities. For example, n is common in both biological growth and resource limitation. However, Biological growth depends on the biological processes, resource limitation depends on the environment. So, the driving causes of these two factors are independent and they are brought together by plus or minus sign. When we are multiplying, it means that these two factors affect each other and they might even share the common drivers, or one may be the driver of the other, or they might be linked together in a nonlinear fashion. So, if we look at this model, log 1 by Bn, as n goes up, log 1 by Bn reduces. So, this is a slowing down factor. This is a factor that is slowing down the net growth. In this sense, it is quite similar to the second factor in logistic growth, Rn square by k. However, Rn square by k is because of environmental reason. It is not because of the rate at which biology is producing offsprings or daughter cells. Here, they are multiplied together, which means the slowing down of n affects the rate at which new consumers in case of economics, or new cells in case of biology, new contaminants such as pathogens in case of environmental contamination reproduce and grow. Alrighty. Now we are going to look at Gompertz model alone and why this interpretation, why and how this interpretation makes more sense. So, in Gompertz model we have in our textbook for this course, the example is given of tumor growth. But please understand that this model, Gompertz model, is used in urban city planning, it is used in environmental scenarios, it is used in marketing, economics. This is particularly useful model when we, in case of economics for example, when we introduce a new product in an economy that has not used that product before. So, if you are introducing a novel product in a market, then typically and the product succeeds, typically we see that the growth of the consumers matches Gompertz model. But to make life little easier, we are going to use the example that is given in the book, tumor growth. So, if you look at this model, how would you, just by looking at it, be able to interpret what the constants A and B mean, what do they stand for, and what do these two factors A n and log 1 by B n stand for? Let us take a look. A n is talking about growth rate, biological growth rate. It resembles first order growth rate of most living entities, in this case tumor cells, in case of economics or marketing it will be consumers. So, here we can say this is growth rate of tumor cells, the rate at which tumor cells grow. Now, let us look at this one. We know as n increases, log 1 by Bn will bring down the growth rate. This is, and if it increases sufficiently, instead of growing, the n will start reducing, very much similar to logistic growth. So, clearly this is some kind of resistance to growth, some kind of dampening of the growth of tumor cells. In case of tumor cells, you can very easily guess who will be or what will be resisting their growth. It is immune system. So, if I ask you in the exam, or if in real life when you are looking at a model and you need to understand what these constants mean, what information is required, or let us say you do get data, you plot the data and this model fits perfectly, how do you interpret what A means, how do you interpret what B means? You need to take some time to think about what are the different phenomena, different factors that are representing different phenomena in my model. So, here for example, we can make a guess, an informed guess, that An is probably the rate at which tumor cells grow, log 1 by Bn is probably the immune system bringing down the growth rate. Now, notice here we could have also used a minus sign between them. We could have written An minus some term that represents immune system. However, the response, the immune response of the body affects the rate at which tumor cells grow. So, the immune system is strong enough, responding really well, the tumor cells will not be able to grow. It is not that we are talking about the rate at which immune system is killing the tumor cells. It is just that if the health of the body is good enough, the number of tumor cells will remain constant because they are not able to replicate, they are not able to grow. And notice here, that is why multiplication sign makes sense, because the second factor affects the biological behavior, the biological driver of the first factor. Plus minus will not do justice to it. Alright, now let us use a geometrical approach to interpret this model. First thing we want to do is find the fixed points. So, to find the fixed points, we have to find out when does dn by dt equal to 0. So, make this whole equation equal to 0. And you can see very clearly that your two fixed points are n equal to 0. So, you do not have any tumor cells to begin with, or you do not have any new consumer to begin with. So, your consumers can't grow in your market. You do not have any pathogen in your water body to begin with. So, pathogen can't grow. N is equal to 0. And then the other one is to make the second term equal to 0. When will log 1 by bn be equal to 0? Remember, natural log of 1 or log of n, log 10 of 1 also is equal to 0. So, basically when 1 by bn is equal to 1 or n is equal to 1 by b, then the growth rate becomes 0. Okay. Now, let us find out the stability of these fixed points. How are we going to do that? Make the phase portrait. On x axis, this is a one dimensional model. So, our first variable goes on x axis. In second axis, we put the rate at which n is changing. We have two fixed points 0, 1 by b. I must say all constants assume they are positive unless mentioned otherwise. I am going to give an example very soon where the constant will change its sign, and with changing sign the behavior of the system will change, but that is not the case here. Here b is positive, so 1 by b is also positive. Now, we need to plot the phase portrait. To do that, we need to know what is the sign of the model when n is between 0 and 1 by b. So, when n is between 0 and 1 by b, we figure out that an is still positive because n is greater than 0, and log 1 by bn, can you take a moment to figure out what the sign would be of log 1 by bn, the second term, when n is less than 1 by b but greater than 0. Yes, you are right, it will be positive. I hope you got that right. So, we know that our plot looks like this. Now, what will be the sign of our dn by dt when n is greater than 1 by b? It will be negative, because this whole term will become less than 1. Log of a number between 0 and 1 is negative. So, this is the kind of behavior we will see. This is also a phase portrait that resembles the phase portrait we have seen in logistic growth, in autocatalysis, and you will see in many other models that we cover in the course. But the difference is that the two factors are multiplied together, they are not added or subtracted. So, right away, right here you should know that quantitatively you should expect differences in the way logistic model behaves compared to Gompertz model. However, there are similarities. So, let us explore the similarities first. When n is sufficiently small enough, let us say n is close to 0, not equal to 0, dn by dt is positive. So, what will happen is the n will move towards right hand side. dn by dt is positive, n is increasing, the flow is towards right side. When n is at 1 by b, dn by dt is 0, there is no flow. When n is bigger than 1 by b, the flow is towards left side because dn by dt is negative. So, if you look at these two arrows I have written on the x axis, they are pointing towards the second fixed point. So, the flow is moving in both directions towards the second fixed point. So, n is equal to 1 by b is a stable fixed point. The flow is moving away from 0 on right side. So, at least on right side we know that 0 is an unstable fixed point. Now, here we cannot interpret this model for n less than 0, which is not required because this model is used for natural objects of which negative does not really exist. So, here we have unstable fixed point 0, a stable fixed point n. If you remember what we have learned from autocatalysis and from logistic model, you should know by now that no matter where we are starting, as long as n is greater than 0, no matter where we are starting, n naught is greater than 0, the final value that you will end up with is the second fixed point, because it is the only stable fixed point in the entire domain of n. So, if you are starting with a very high n value, The n will continue to reduce because dn by dt will be negative until it reaches a fixed point. If you are starting with a low value, a non-zero low value, dn by dt is positive, so the number of tumor cells will end up at n. So we know this, that the final amount of n, final number of n, concentration of n, in case of tumor cells, final size of the tumor or final number of tumor cells in the body will be equal to 1 by b. So qualitative questions like this can be answered without going into quantitative analyses. Now, before I tell you what we are going to do in next lecture, I want to spend a minute here looking at the second fixed point. So in case of tumor, because that's the example we have taken, the final size of the tumor is 1 by b, number of tumor cells. So you know that in this system, if you have data on how tumor is growing, let's say you have a system in which pathogens are growing and you know that it is following Gompertz model really well, or you are in medical modeling field, which many engineers do end up working in, by the way, many mathematicians end up working in that field. If you know how the size of the tumor is changing and you can fit this Gompertz model, you can predict what will be the final size of the tumor. When will the tumor stop growing? So notice the number of cells in tumor or the size of tumor, depending on how I define my units of n, is 1 by b. So since I know that log 1 by b n gives me an idea of the immune response, I can already say that b has something to do with the immune response, something to do with the health of the body. In case of pathogen infiltration in gut microbiome or in environmental microbiome, b might have something to do with the resilience, the functional and taxonomic resilience in the system. Okay, now let's think about how to solve this question quantitatively. Now quantitatively you can go on and integrate it and then try to figure out what your model looks like and then plot the model, but until you are able to calculate how n changes for every little value here as n increases from a small value, and that will be very calculation intensive, we can also use a very simple quantitative approach to understand how the model behaves. So in the next lecture I am going to cover the quantitative approach on how we can minimize our calculations and still understand how the system works. That is typically helpful for systems in which qualitative approach does not work. And I know I admit that I am a big fan of qualitative approach, but I do know that if a unique solution does not exist, or if the first derivative of our rate equation is equal to 0, qualitative approach really is not very reliable. In some instances, qualitative approach fails completely. So we do need to go into quantitative approach. So in the next lecture, we are going to look at the same model and simpler models. We'll start with simpler models and eventually build up to this model and see how we can revisit the models we have studied, but using a semi-quantitative approach. That's all for today. See you in the next lecture.